Welcome to another statistics lesson. So last time we saw probability, we defined it, we had a bunch of examples on how to calculate it or determine it. And this time what's going to be new is that we're going to start looking at what's called compound, give me a pen, compound events, or you could say compound outcomes. I was using outcomes, I think, pretty much exclusively last time. Events, it's the same thing. You'll hear me use both words interchangeably. So anyway, compound events means something happens and something else happens. I want both of these things to happen. Like two things in a row, kind of like you're going to flip a coin twice or something. Two things in a row. I want the heads and then I want the other one to be heads. Something like that. That's what we mean by compound events, especially, and today we're focusing on this and that happening. And we're going to limit ourselves to what's called independent events. You might remember independent events simply means one event has no bearing whatsoever. What happens here has no bearing on what happens there. They're just completely independent events. Anyway, before we get to that, let's just recall our definition of probability that we saw last time. This would be a good spot for you to simply ask yourself, how would I define probability? If I wanted to define it carefully, what would I write? What would I say? Maybe something like this. The probability of event A, so I'm using the word event again. The probability of event A, or outcome A, you could say, is the ratio of, remember they're fractions. We make a ratio. We put something on the top and something on the bottom. On the top, we put the number of outcomes. Now I'm using the word outcomes, whatever. The number of outcomes that we identify as belonging to A. Is this a heads? Sure. Is this a heads? No. If it's a heads, it belongs to A, or whatever. So anyway, number of outcomes we identify as belonging to A, so to speak. The reason this belonging, this kind of word actually works is because in math they typically think of outcomes or events as sets of things that might happen, and so that's why we say belonging to A, it belongs to set A, but we don't have to worry too much about this lingo stuff. It's just, what is it? It's the number of outcomes that we identify as A divided by the total number of outcomes, right? Total number of possible outcomes. Now, it's good to have the sentence and understand the sentence and so on, but as a nice shorthand, we can just write this nifty-difty formula. So there's our notation. The probability of an event A or an outcome A occurring is, you take the number of outcomes that you would count as A, you take the number of, total possible outcomes, right? And there was one important thing to keep in mind. Do you remember what the one important thing is to keep in mind? You must count equally likely outcomes. Every outcome that you're counting must be equally likely. It's very important because this is a fraction, right? And remember, fractions, you have to cut things up into equal sized pieces for the fraction to make any sense. Well, it's the same here. For this probability fraction to make any sense, all of these outcomes that we're counting, they must all be equal size, so to speak. In other words, equally likely. And we have a nice PS that we could add here. Do you remember anything else that was significant about probabilities? Well, how about this? They always come out, they have to come out between 0 and 1. Because 0 means impossible, inconceivable. And 1 means certain, it's a sure thing, bet the house. Okay, so probabilities always come out between 0 and 1, and often we express this fraction, we reduce it for one thing, but we often express it as a decimal and or a percent or so on. Okay, so that's what's going on. So, that was a good exercise. Okay, now let's get to the topic at hand. We want to determine the probability of two things happening in a row, this and then that. So example, Biff flips 2 fair coins. By the way, I could put this in green. This word fair is kind of like code. Code for, what should I say, equally likely outcomes. In other words, getting heads or getting tails is going to be equally likely, which is good. That's what we want anyway. So he flips 2 two fair coins, not one, two fair coins. And we want to know what's the chance he gets both heads. Well, think about what's going to happen here, right? We have a first coin, and that coin will come up either heads or tails. And then we have a second coin, and the second coin is going to come up either heads or tails. So what all's possible here? Well, we might get heads on the first coin and then heads on the second coin. That's possible. We might get heads on the first coin and then tails on the second coin. That's possible. We might get tails on the first coin and heads on the second coin. That's possible. We might get tails on the first coin, tails on the second time. That's possible. Now, what you might want to do instead of all that, those crisscross arrowy things, in fact, what I think I'll do is I'll shrink this down. Shrink yourself. Come on, shrink yourself. Shrink yourself. And move over here too. Okay, cool. What we usually do or often do or can do is something called a tree method. And so I want to, actually, we should label this and everything. The tree method. It's a nice way for mapping possible outcomes. Keeping track of what could happen. And it goes like this. It's almost like the many worlds theory of physics. So there you are, or there Biff is. Biff is right there. Biff is in his universe. He's all happy as a clam. But the universe for Biff is about to split into two alternate realities. In the first alternate reality, he flipped the coin and it came up heads. In the second alternate reality, he flipped the coin and it came up tails. So these are the results for the first coin, right? Two possible results, two possible universes, if you will, for the first coin. Either it came up heads or it came up tails. Okay. Now pretend that he went this way, that in his universe, he got heads. Well, now what happens? Well, now in that universe, he's going to flip the coin again, and it's going to split again. This is the nature of the many worlds theory of physics, which sounds crazy to me, but whatever. So the idea is that, you know, now we have, he could end up in this universe where he flipped the heads and then he flipped the heads on the second coin. There's another universe that ends here where he flips the heads on the first and the heads on the second, right? These are all possible outcomes, I guess, in the end. And by the way, if he flipped the tails first, on the first coin, he could get a heads or a tails on the second coin, right? So this is the second coin. And then we have, well, let's get green again. We have our possible outcomes right here. So this path, he got a heads and then a heads. We might write it this way. In this path, he got a heads and then a tails. This path through the multiverse. This path through the Spideyverse, whatever you want to call it. He got a tails and then a heads. Uh-oh. I want to erase that. Okay. He got a tails and then a heads. And then in this Spideyverse, he got a tails and then a tails. So these are all the possible outcomes over here. There's 4 of them. 4 of them. And so we can conclude, back to blue, that the probability that he gets 2 heads in a row, which I'll just notate it that way, that's a nice shorthand, I like it, would be, well, you would count the number of outcomes that are heads, heads, and then you would count the number of total outcomes. And these are all equally likely, right? It's equally likely to get a heads or a tails at every juncture here. So because it's equally likely, this is fine. And I can say, well, there's only one way to get heads, heads, and it's put a 1 on top, and there's 4 different things that could have happened. The 5th thing is I could have scrolled by accident. Okay, so anyway, so it's a 1/4. Boom. It's a 1/4 chance of getting both heads. Okay, so that's the tree method. The tree method is worth playing around with because it helps you kind of follow the action and stuff. Okay. And now for the main event. Or, if you don't want to get that involved, well, this is a wonderful, 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 wonderful shortcut. You can think like this. Well, on the first coin, the probability of getting heads is 1/2. And on the next coin, the probability of getting heads is 1/2, right? So the probability of getting heads is 1/2 times 1/2. And what's 1/2 times 1/2? It's 1/4. That saved a lot of work, didn't it? This is called multiplication rule which you saw in the title to this little lecture here. This is called the multiplication rule. And there's actually two versions of it. For today, we're just working on independent events. So every coin flip has zero influence on every other coin flip. So this is for independent events. So keep that in mind. Independent events today. No coin flip affects the outcome of any other coin flip. Okay? Now, don't you love it? This is the multiplication rule. You want to do two things in a row? You want to get heads twice in a row? Just take the probability of heads on the first times the probability of heads on the second. And of course, they're both the same. They're both half. And multiply them. And you get 1/4 and you're done and you go home. Well, hopefully you don't go home. Hopefully you stick around for the next example and you say, what else is going on? Okay, here's another thing that's going on. Bonnie's going to flip 3 fair coins. Fair, again, means all outcomes equally likely. Yay, we like that. She flips 3 fair coins. Find the probability she gets heads 3 times in a row, so I'll just write this out again. The probability of heads the first time is 1/2. And then the probability of getting heads the second time is 1/2. And then the probability of getting heads the third time is 1/2. And it's all independent events. And what does that mean, by the way, if they're independent? Well, I mean, no one result affects any other result. That's what it means. But I mean, why is that good? It's good because it enables us to just kind of use probabilities. We can use the multiplication rule is what it means. We can actually multiply 1/2 times 1/2 times 1/2. You know what? I wanted to write that a little bit differently. I wanted to write it this way. I wanted to write, so the probability of getting heads 3 times in a row is 1/2 times 1/2 times 1/2, which is 1 in 8. There's a 1 in 8. And you could try it if you want. 1 time in 8, you should get, on average, over the long haul, no guarantees, you should get heads. You should get 3 heads, 1 time in about 8. Cool. Here's our multiplication rule. I hope you dig it. So that's page 1. Now how could I possibly have filled up 3 more pages of examples? Well, let's see what's going on here. Now Bess is going to flip 10 fair coins. What's the probability that all of them are heads? Well, I hope you're catching on here, right? She's going to do this 10 times in a row. And so maybe I'll write it this way. I'll say heads, and heads. 10 in a row, right? Now you know it's going to be, the probability is 1/2 on the first, 1/2 on the second, 1/2 on the third, and let's not write this all out. Let's just say that it's 10 times. And I got another little shortcut kind of thing for you. We could just say, well, it's a 1/2 and she has to do it 10 times in a row. See? Exponent. The exponent is a shortcut of saying I'm multiplying 1/2 10 times in a row. So let's make that 10 look a little bit more like a 10. There we go. And if you ask Mr. Calculator what that is, Mr. Calculator will say it's 1/1024. Now if you make that a decimal, either hit the SD button if you have a Casio, or go 1, well, might as well write it, 1 divided by 1024 to get yourself a decimal. Your calculator will probably say something like this: 9.7, what do I got here? 65625. And my Casio then says this. It actually says this over here. It says times 10 to the -4th. Your calculator might say it a little bit differently. Your calculator might just have a -04 off to the right, or it might even have an E -04. There's all kinds of ways you can do it, but what they all mean is they mean scientific notation. So I'm pretty sure you've seen that somewhere before. So remember, the idea is you have to slide your decimal, because that's a -4, you have to slide your decimal to the left 4 places. 1, 2, 3, 4. And I get a point 0.00097. I'm just going to round it to 66. That would be the decimal form. So because of this -4, I had to go to the left 4 places to make that into a real decimal without the scientific notation. Now if you want the percent, remember decimal to percent, ooh, that's not a P, that's not a, come on you. Okay, decimal to a percent, you would go to the right 2 places no matter right? So this has got nothing to do with scientific notation. This is separate. A decimal to a percent, you have to go to the right two places. So if I go back to the right two places, I got 0.09766, I guess, as a percent. So it's not very likely is what we're trying to say. However you want to express that. I actually, in this case, I like the fraction. 1 chance in about 1,024. So not real likely. It's going to take you a while if you want to keep trying until you get it. Or you expect it to take a while. Nothing's guaranteed, right? It's all random. Random does what it wants. Okay, so that's cool. We got this exponent shortcut. Okay, bam, bam. And then example 5, Florida getting hit by a major hurricane. Okay, why don't you try these two? Pause the thing, pause the video. Try both of those examples right about now. And then replay. Okay, here we go. So they're all independent events and stuff, independent outcomes, however you want to say it. So the probability of getting I kind of don't want to write this, 666, just because it looks like one number, 666. So I'm going to write it this way. The probability of 6 and 6 and 6, getting 3 6s in a row is, well, the chance of getting a 6 on a 6-sided die would be 1 in 6, right? Because only one of those faces has a 6 on it. And since we're doing it 3 times in a row, I could multiply times itself 3 times, or what means the same thing, I could put an exponent of 3 on there. And that comes out to a nice fraction of 1 over 216. And if you turned it into a percent, you'd get something like 0.463%. Okay, cool, right? Cool. No tree diagram, no muss, no fuss. Okay, this one's kind of practical, especially if you live in Florida, I guess. So the probability of Florida being hit by a major hurricane in any given year, which means this year, next year, any particular year, is 29%, which sounds like a lot, but then again, we're always hearing about hurricanes hitting Florida, aren't we? So the probability of Florida being hit by a major hurricane in any given year is 29%. Cool. Now, find the probability that Florida is hit 3 years in a row. Now, we'll assume that any particular year the hurricanes are independent. How many hurricanes you had this year doesn't really have a bearing on how many hurricanes you have next year. There's no direct tie between the two. It's not like Hurricane, I'm trying to think of a name, Hurricane Janet or whatever, in the year 2024. Because of that, we had Hurricane, Biff in the year 2025. It doesn't work that way, right? Weather is always up, the whole atmosphere is always updating itself pretty much second by second, or at least hour by hour, or day by day, or whatever. What happens this year? So anyway, 3 times in a row, huh? Okay, you want 3 in a row? Well, the chance of doing it 1 year is 0.29. You want to do it again, you'd multiply by 0.29. You want to do it again, you'd multiply by 0.29 again. So 3 times in a row means 0.29 times 0.29 times 0.29, which is 0.29 to the 3rd power, which is 0.0244 on your calculator, which if I slide my decimal over, it's about 2.44%. Okay, now I want to add a little tip for you. This can be handy when you're thinking about probabilities. So I'm going to say tip. 2.44%, yeah, what do we know about that? We know it's kind of small, right? 0.0244, what do we know about that? Well, we know it's kind of small, right? Okay. It's hard to really think about how big that number is. So sometimes what's a good thing you can do is you can try to think in terms of, so I'll say sometimes it's easier to ask, let's put it that way. This is 1 chance in how many? This is 1 chance in how many? The percentage is telling you it's 2.44 chances in 100, because that's what percent means, in 100. 2.44 chances in 100. Well, that doesn't sound so bad, but anyway, this is 1 chance in how many? Now, how can you do that? You would do it this way. I'd say 0.0244, take the decimal, is 1 chance in, and what we would actually do is you would go like this. You'd flip it over. You take the 0.0244 and flip it over, take its reciprocal. And when I do that, did I do that? I hope I did that. I did that. It's about 1 chance in 41. And that, I think, is easier to help get a grapple on what these numbers are telling you. They're telling you that one try on 41, you will get hit. You'd expect to get hit, not that you will. You expect to get hit by a major hurricane in Florida 3 times, 3 years in a row. 3 years in a row. So once this year, once next year, once next year. 1 chance in 41. That doesn't sound like an amazingly hard thing to do, does it? I mean, sometime in your lifetime, it might happen. No guarantees. But over the long run, right, we expect it to level out to about 1 chance in 41. I mean, assuming that this number is correct and all that. So 1 chance in 41. Now, why is it useful to figure this out? Well, just assume that actually happened. Let's say we got hit by a hurricane 3 years in a row. Well, what if somebody says, oh my God, global warming is really getting out of control? Okay, well, whatever you think about global warming, would that be evidence? Would Florida getting hit 3 years in a row be evidence of global warming? Well, this says no. I mean, or here's how I should say it. You can't say that based on this. You can't say that based on the fact that Florida got hit 3 times in a row. That's not evidence. Why isn't it evidence? Because it's natural to expect that one time in 41 years, which is like everybody's lifetime. It should happen sometime in your lifetime. I can't think, I don't keep track, but I should look that up. When's the last time Florida got hit 3 times in a row by a major hurricane? I don't know, but you expect it to happen. So anyway, it's a way of, you don't want to just believe everything you read or everything somebody says. You want to always be like, trying to understand it. Like, where does this come from? Is this really true? Should I believe it? Should I worry? Stuff like that. So anyway, that's a really good way to make sense out of these statistics sometimes. Because if someone said, oh, well, it is a 2.44% chance, I don't think you're winning the argument because nobody really knows what that means. But 1 chance in 41, people know what that means. Okay. All right, moving right along. So now we got a different problem, different-ish. We're going to walk up to 2 random Americans somewhere in the country. We'll just randomly throw a dart at a map of the U.S., go there, go to that town, grab somebody, and say, hey, when were you born? And then we'll do it again. We'll throw a dart with a blindfold and go to that town and grab somebody at random and say, hey, when were you born? I'm saying that because that would be a very good sampling technique. Random, random, random. So we're selecting people at random. So what's the probability? Part A. What's the probability both are born on January 1st? Well, what you need here is you need probability that this guy was born on January 1st and the next guy was born on January 1st, right? So it's independent, right? There's, one guy's not going to affect the other guy's birthday, I don't think. So we're going to say it's basically take the probability someone's born on January 1st and multiply it by the probability someone's born on January 1st. And so what is that? Well, let's just assume there's 365 days in a year. We'll forget about that whole leap year thing just for the sake of getting an answer here. And it'll be a good answer. It'll be very close. But anyway, 1 in 365 for the first person, and it's also a 1 in 365 that the other person would be born on January 1st. Now, I am assuming that people are born, people's birthdays are, equally distributed, that you're just as likely to be born on January 1st as you are January 2nd. I don't know that that's true, but it's an assumption we can make. And anyway, what does this come out to be? It comes out to be, well, after I slid the decimal around, scientific notation, and then to the right 2 places to make it a percent, I got a really low number. It's like 0.0000751%. So the decimal would be 0.000, and remember, to get from a percent to a decimal, you would go this way, so we'd have to put a couple more zeros in there, which is 1 chance in, well, I'd have to take 1, I'd have to divide by 0.0000751, boink. It's like 1 chance in, holy cow, it's like 1 chance, roughly speaking, in 133,000. I rounded it off, but it's not likely. Okay, 1 chance in 133,000, not likely. Let's look at question B. What's the probability they both share the same birthday? Notice we're not talking about any particular birthday. We're not saying both January 1st. We're not saying both July 30th or whatever. Not any particular birthday. It's just that they're the same. Okay. Well, we're going to do two things. We're going to ask the first guy, what's your birthday? And what do we need the answer to be? Doesn't matter. Who cares? Who cares? Doesn't matter. We don't care what the birthday is. What we care is that when you ask the second guy, it has to be the same, or it has to match the first guy. Match the first guy's answer, I guess is what I'll say. So, the first guy can be born on any of those 365 days. We don't care which one. Basically, it's a probability of 1. He's going to be born. And there's going to be a day assigned to it. So the first guy, who cares? The second guy has to be the same. Now, that's only a 1 in 365 chance, right? Now, by the way, 365s are going to cancel on the diagonal here. You're going to get a 1 in 365, which I made that into a percent too, and I got 0.274%. Much more likely. I invite you to change that into 1 chance in how many? 1 in, figure it out. 1 in. You should get, if I round to a number, well, that was kind of a needless question, wasn't it? We've got it right there. 1 chance in 365. What I actually did is I slid the decimal back 2 places and I took the reciprocal, which again was really not necessary, but cool. What do we got going on here? The probability a particular product is defective is a whopping 20%. Well, that's bad. But if you look at the bright side, it's 80% that it's going to be okay. So, okay, 80% chance that it's good. You're going to order a box of 5. How many do you expect to be okay? Well, if 80% of them are okay, you expect 80% of the box or whatever. You expect that. Now, expecting doesn't mean expecting as in, oh, it's really going to happen. It just means that according to the laws of statistics, if you kept ordering a box over and over and over at random for a long time, then over the long haul, you would expect, no guarantees, that 80% of these boxes, of these, not boxes, of these products, or no, 80% of the box, 80% of the products would be good. So, what is that? Well, it's 80% of, how many are we getting in the box? 5. So what is 80% of 5? Well, you take the 80%, you turn it into a decimal, back 2 places, multiply by the 5, and you get 4. And so 4 should, in quotes, be okay. If you randomly grab a box of 5, you expect 4 good ones. Cool. Now, part B says, what are the chances all of them are okay? All 5 are okay. Well, here you have to imagine taking them out of the box one at a time. Taking them out of the box one at a time. And what you need is for all of them to be okay. All 5 of them to be okay, which means you need the first one to be okay, and then you need the second one to be okay, and then you need the third one to be okay, and then you need the fourth one to be okay, and then you need the fifth one to be okay, or you could have said it this way, 0.8 to the 5th power, which when you work that out, you get something like 0.328, which is like 32.8%. So there's almost a 1 in 3 chance that they'll all be good. You expect 4, again, over the long haul. You might get 3 in this particular box. It's even possible none of them will be okay. Probably not likely, but it's always possible. Randoms like that. But 32%, about 1 chance in 3 that they'll all be good. Okay, one more example. I wanted to bring up unfair coins. Unfairness can happen. Unfair just means that it's not a 50-50 of getting heads or tails. It's not fair. Brenda has a specially weighted coin. It's going to come up heads 70% of the time, which means tails 30% of the time, because it's got to be one or the other, right? So it's heads 70%, tails 30%. And now we want to figure out, okay, so now what's the probability she gets both heads, or heads and then tails, or tails and then heads, or tails and then tails? So we're going to work out all these different possibilities here. Now I'd like to go back to the tree diagram again, just for fun. So here's this Brenda. Okay, here's Brenda in her universe, her multiverse. And she's about to flip a coin, and boom, she splits into two possible micro Spideyverses, whatever you want to call it. So this is a first flip. She either gets heads or she gets tails. Okay. Now, if she goes into the heads Spideyverse, that's going to break into two Spideyverses again when she flips the second coin, either heads or tails. This one, either heads or tails. So that would be the second flip. And so the possible outcomes, and actually we saw this on page 1, right? The possible outcomes are she could get heads and then heads, she could get heads and then tails, she could get tails and then heads, she could get tails and then tails. What's different? Well, what's different is, and I'll put this in like a fuchsia, but hey, these are not all equally likely outcomes. These are not equally likely. Why not? Because you're more likely to go towards heads than you are to go towards tails. And then again, she's more likely to go towards heads than to go towards tails. So it's probably more likely that she's going to end up here than any of these other places. See what I mean? It's not all equally likely. So you could not say the probability of heads is 1 in 4 because, look, there's 1 out of 4. It doesn't work that way because they're not all equally likely. So I'm going to go like this. Maybe I'll do it this way. Probability of heads is not 1/4 exclamation point. We have to do something else. See, the thing is, the chance of getting heads on any particular flip was 0.7, which means I could sort of put that on the path here. Say the chance of taking that path is 0.7. The chance of taking this path towards tails is 0.3. Over here, the chance of taking that path towards heads was 0.7. The chance of taking this path was 0.3. Towards heads, 0.7. Towards tails, 0.3. So you see there's different probabilities among the different branches. Again, it's not all equally likely. But these are independent events, which means we can use the multiplication rule. We can use the multiplication rule, so that's the good news. We're going to use the multiplication rule. So, the probability of heads would be what? Well, you'd have to figure out what's the chance I get heads times what's the chance I get heads on the second try. It's a 0.7 on the first try. It's a 0.7 on the second try. You get 0.49. So this is actually 49% likely. It's almost a 50-50 that she's going to get 2 heads. And we can work out the other ones too. So I think the next question was heads and then tails. Well, you take the probability of heads on the first times the probability of tails on the second. Heads on the first is a 0.7. Tails on the second is a 0.3. Those multiply out to 0.21, which means there's a 21% chance of getting heads than tails. Next up, tails than heads. Well, that means you have to first get tails, and you have to next get heads. And so tails is a 0.3, heads is a 0.7. That also comes out to 0.21. Put that up here as 21%. Last but not least, the probability of getting tails twice in a row would be you take the probability of tails on the first flip times the probability of tails on the second flip. So that's a 0.3 on the first flip, it's a 0.3 on the second flip. You end up with a 0.09, which I'll put that up here as a 9%. Now notice that these do all add up to a perfect 1.00, which is of course the same as 100%. Something's going to happen. One of those 4 things is going to happen with 100% certainty. Which one? Well, most likely going to get 2 heads. So if she's playing a game where you have to get 2 heads, these are good dice. It's going to be like a 50-50, and everyone's going to go, wow, how did she do that? Cool. I think that's basically what I wanted to say. But actually, no. One more thing that we could note. I'll just put a PS here. One way we could summarize these results, and this is kind of to plant a seed in your mind. One way we could summarize these results is to say 49% chance both are heads, right? That's what that says. 9% chance both are tails. That's what that says. And basically, these are both, you could describe these both in the same way if you say one of each, right? Because here we got the heads and then the tails. Here we got the tails and then the heads. Okay, so they are different technically, but they both, you could look at them both as saying one of each. So 21% and 21% is 42% chance of one of each. Really cool. Okay, so I think that'll do it for this one. Yep. How long did that one take? 35. I'm getting better.